So first off, thanks everyone for joining this panel. The goal here today is to talk about zk-SNARKs and also the future of crypto. I'm Howard, I'm a co-founder for Dekrypt, and with me here is also Izaak, who is a co-founder for O1 Labs, Coda protocol, and Arthur Breitman, who's a founder for Tezos. I guess the best way to get started really is to first just define, what is a zk-SNARK, and also just say a little bit about why you guys are so passionate about this technology.
Who should take that? I don't know.
Oh, either of you or each of you, really, probably.
Arthur, you can go ahead. Okay, I can start if you prefer. So yeah, what is the zk-SNARK? Well, it's basically a way to convince someone that you ran some complicated computation that may have required a lot of data, inspecting a lot of data, without them having to rerun that computation or see that data in such a way that you leak nothing to them about the data that you were computing on, except for the output of the computation. I guess in a nutshell. Well, as to why it's important, I mean, okay, of course, Howard, so this is, I guess, for the benefit of everyone. If you want to build systems that are sort of truly verifiable from the point of view of the end user, it's an essential technology, because otherwise it means that if you want to build a verifiable system, that you're limited to the computing power of the weakest, computationally participant. Oh, and as to why, you should want to build verifiable systems or whatever, there's actually a really, let me just plug this guy's thesis. If someone Googles accountable algorithms, this guy, I think his name is Joshua Kroll, or something like that, wrote a great thesis on why this is a good concept.
Arthur, do you want to share a little bit on
I'm very sorry. My sound wasn't on, and I didn't realize that this thing was going on already. So my apologies. Could you repeat the question? I'm happy to address.
Yeah. We're just getting things started off, and the main thing is just to kind of define convention here. So first off, how do you define a zk-SNARK for yourself, and also what gets you excited about this technology?
Well, definition of zk-SNARK, I think it's a bit holistic. I'm never sure if it points to a specific implementation of a zk-SNARK, like the original ones which were published, which were based on the approach that's used for Zcash, for example, or if it's related in general to all zero knowledge proofs and so on and so forth. So I'm not sure exactly what to encompass in zk-SNARK. Basically, I guess what I would consider the zk-SNARK is anything where you can verify general computation, and then where you have good scaling properties, in a sense that you get a proof that is going to be short, non-interactive, and very quick to verify, and I will tell you is very high probability that yes, I do know a witness to a given language, for example. So that would be my definition.
That's awesome. So currently zk-SNARKs are really it's a separate line of development from blockchains, and we're starting to see, as you guys rightfully see, that zk-SNARKs are actually being used in a lot of different protocols that are being built for blockchain protocols. And I'm curious, from your point of view, what makes it so interesting to use zk-SNARKs in blockchains?
Well, there's two aspects. And first of all, the reason why zk-SNARKs, as opposed to other constructs that have for verifiability that have been created before, is the constraints of the blockchain means that you really don't want a scheme that's interactive, because it's expensive. You really want something that's concise, and also you want something that's publicly verifiable. So that's asking a lot, and the SNARKs deliver on all that. I see broadly two categories of application for SNARKs. The first one, and the original one it was used for, is if you want to have some sort of privacy. The difficulty is that the idea of how Bitcoins and other cryptocurrencies solve the double spend problem is by saying, okay, the way we don't double spend is that we mandate that any valid transaction must be publicized and known by everyone. That's how you do it. And so when I receive a transaction for you, it only counts if it's on this ledger that everyone knows, everyone is in sync with. It's a very, very strong requirement, and that makes privacy very, very hard, because if everyone can see every transaction, how do you make it private? And zk-SNARK is basically a way of doing that. And as we've seen, for example, with Zcash, where you get a lot of privacy. Basically, you make a transaction and you say, well, you know what, at some point I had some money, and now some amount of money is going to someone else, but you don't learn anything else. So that's one aspect. And the other aspect is for scalability and efficiency. So right now, in order to for everyone to understand this ledger, especially if you're going to have smart contracts, for example, which involve computation, you're going to have different parties who must agree on the content of the ledger. And in order to do that right now, they all repeat the same computation, which can be a little expensive. And if instead of having everyone compute everything, we just have the parties that wants to submit a transaction compute the outcome of their transaction, and then just submit that to the network alongside with a proof. So you can have, right now, all smart contract platforms like Tezos, Ethereum, they use a gas model where basically, you send a piece of computation and you say, I promise that my computation is not going to exceed X many steps. And then you have something that will re-execute it and count the steps. Instead of that, you could have computation that can go on for as many steps as I want. I run the computation on my machine, and then I just send a proof to the chain saying, hey, that was a computation and this is the result. So you get a lot of benefits in terms of sort of communication between chains. And I think like the privacy is super important, but most of the exciting research around SNARKs, I think, is going to be around this idea of I'm doing computation and then I use that to communicate the outcome of a computation in an efficient manner. And in that case, you care more about the SNARK part than the zk-SNARK part.
Oh, Izaak.
I was just going to say, of course, that's a big part of what we're doing in Coda is, making it possible for all network participants to sort of verify the chain without having to redo the computation that has happened on the network so far. And often when I talk about SNARKs, I will just say SNARK and not zk-SNARK, I guess, for that reason. I guess I also want to just mention maybe briefly, to build on what Arthur was saying, it's interesting, what you said is true, of course, that it's a separate line of research from, general blockchain research or whatever. But, I guess in some ways, most of the theoretical work about SNARKs had been done, a long time ago. Theoretically, it was understood that SNARKs were possible and so on. A long time ago, and yeah, in I guess I don't know when the PGHR paper is from, but at some point in the 2010s, these pairing-based SNARKs started going, and definitely a lot of the work, as far as I can tell, that happens nowadays is, if not driven by blockchain applications, at least all the authors probably have it in mind when they're writing their papers, if I had to guess, based on the people involved.
Yeah, and also just for those who are on this panel and listening in and want some clarification, the SNARKs are really, it stands for succinct non-interactive arguments of knowledge, and what that really means is that you have something that's very succinct, so it's very short here in terms of time to verify, and also just in size for the proof. And it's also non-interactive, meaning once someone generates a proof, the person who's verifying doesn't need to communicate with the proof from then on. They just look at the proof. The SNARK versus zk-SNARK here is really delineation between what is considered, a public, a proof on public data versus like a proof here effectively on something that you're trying to hide, which is called the witness. And the witness here is effectively what you're trying to keep private. The SNARK part of zk-SNARK is actually very powerful, and I think that there's whole directions that are not being considered yet for its use in blockchains for scalability. For one, I think with Coda, this is the of actually using SNARKs to get a much more compressed and also a much more realistic representation of a block, or even just an entire chain of blocks for future light client devices, very low-end devices like mobile and whatnot. And I'm curious, from your guys' perspective, how do you see that evolving, and also what other areas do you think zk-SNARKs will help with blockchain scalability?
Yeah, I mean, I guess I think there are a lot of ways. One is just like what is happening now in Coda. Another is, I think, what Arthur mentioned about doing some long offline computation and just posting an update to the blockchain. I think that's an important mode of operation. I guess another thing, which is maybe not strictly blockchain, but it's probably an underexplored application area that I think could be aided by blockchains, is making the kinds of programs that people interact with already, social networks, whatever, but with stronger privacy and verifiability properties. So I think that would be a very interesting application. I mean, I think it pairs well with blockchains in terms of censorship resistance, but even in like a centralized regime, I think that would be a good and interesting application for SNARKs that basically, to my knowledge, no one has, considered.
That's fair. Besides just the scalability piece and the privacy piece, Arthur, you actually touched on a little bit earlier on just the usage for communications between blockchains, a little bit about just it helping with interoperability. I'm curious, how do you envision zk-SNARK proofs as a mechanism for enabling interoperability?
Yeah, so generally when you have chains communicate with each other, the difficulty is that it's not just, you're not just like shuffling around information. Shuffling around information is easy. You want to show one chain that you are using not just like a piece of information from another chain, but from like the other chain, right? From the canonical of the chain. And the way that blockchains ensure unicity is through the use of a consensus algorithm. So if you give me the content of a Bitcoin block, what interests me is not so much that this is a block and this is a Bitcoin-like block. I want to know that it's a block in the Bitcoin blockchain, for example, or in the Tezos blockchain, and so on and so forth. And the way you can do that is you can have light client proofs, for example. So in a light client proof, you're going to get just a few block headers, and just from that context, you can infer that it's probably on the main chain. But with zk-SNARKs, you can do something better. What you can do is, if you have a side chain that you can have a proof that, I took this chain and verified it from the Genesis block, which is something that Coda is doing. And then you say like, okay, now here's a proof that yes, this block belongs to this chain. If you follow the rules from the beginning, you can port it to the other chain and have this property. It's unfortunately something that's a little it's less meaningful if you're doing proof of stakes and you're doing proof of work in some sense, because in proof of stake, you're always going to have to contend with weak subjectivity. And so in some sense, the ability to prove everything from the Genesis block becomes less valuable, but it's still hard to kind of fake a chain like this. And so there's some value in verifying everything. So that's, like talking between chains is a thing. Sharding is another one. So in sharding, right now you see like sharding proposals, like for example, in Polkadot, where you have, I think they call them fishermen, where you just like look at blocks which are being produced on one of the shards, and then they pose the hashes of these blocks. And the idea is that, in theory, anyone can come in and say the state transition function that you applied here is invalid. And then you have this protocol, where this interactive protocol, where you do binary search on the trace of the thing. It's very, very heavy. If instead of that, you could just post a SNARK showing like, yeah, the state transition is valid, don't worry about it. Then you still have an issue, which is that, you still have to rely on the fact that those people are not going to be bribed to pick the wrong block, like a block out of sequence, and you have to rely on favors a specific block, and you have to rely on data availability. Like data availability is a really hard problem, but at least you can kind of like crush the safety of the state transition problem with SNARKs. But it's kind of similar to what I was saying about smart contracts. You can look at this sharding system as just like having these big smart contracts that look at these outside chains.
That's really interesting. I think that the vision for like getting us to verifiable computations using SNARKs is very powerful. Like it's obviously been a pipe dream of a lot of researchers in the field, and for me, it's like I look from like a research perspective, and then how into practical usage. And for me, like I'm curious from your guys' perspective, what you think are some of the biggest barriers to getting it there. Like, for me, like I feel like one of the core limitations right now is just the lack of a simple programmable language to represent computation or represent state, so that you can easily make these proof-based arguments about it.
Yeah, I mean, there are definitely a lot of limitations. Let me try and list all of them. So one is definitely, or all of them that I know about. One is definitely, as you mentioned, the tools aren't so great. So there are a few, SNARK programming languages. Snarky, which we use, is one. There's also Socrates. There's Sean Bo's Bellman library, and there's also xj-SNARK, which is interesting. But yeah, as you mentioned, the tools aren't that good, and in some sense, the tools could be really good. I think even probably today, in some sense, they could be good, except that if you sort of took a straightforward high-level programming language and compiled it in a naive way into the kind of representation, machine code representation that the SNARK constructions need, it would be insanely inefficient. So maybe in some sense, that leads to the next problem, which is really efficiency, which is okay, but you still incur like a huge factor in comparison to doing the computation natively. So we're not going to be running all of our computations in zk-SNARKs anytime soon unless we improve the efficiency dramatically. So
do you think we'll ever reach hardware-based implementations to try to optimize that, or are there other ways? Do you think we'll reach like hardware-based optimizations or other types of optimizations to improve that?
Yeah. So right now we're running this SNARK challenge. Anyone can Google SNARK challenge. We're encouraging people to submit GPU-based implementations. The SNARK prover is an extremely parallelizable algorithm. So we expect to get a really huge speed up from that, but it's going to be maybe 2 orders of magnitude optimistically, which is still a ways off from the speed of native computation. So, but yeah, hardware-based algorithms. I mean, I last time I heard, I think there's one person who's working on something with FPGAs. That sounds very interesting. Yeah, I guess like one other. Right. So there's the tools. There's the efficiency. Yeah. I mean, at the end of the day, maybe it all really comes down to efficiency, because we could have, well, or rather maybe there's a trade-off between the simplicity of the tools and the efficiency. Like we could have really simple, easy to use tools at the cost of efficiency, but or we could have hard to use tools but have good efficiency. So anyway.
Yeah, I'm gonna say the same thing. I think the main bottleneck right now is efficiency. It's very, very, very low. And so if you're trying to do like just a simple circuit that's going to do one thing, and then you can even hand tune a circuit, you're going to get something. But if you want to have something that's anything large, the times are going to be prohibitive. One of the nice things is that you can potentially outsource that. So especially if you don't care about the zero knowledge part, you can just send your computation to someone and who's going to create the proofs for you. So that's potentially like maybe that someone has like these FPGAs in their basement and they're doing this. So that helps. But at the end of the day, I do think we need breakthroughs in efficiency for SNARK to become more usable. One avenue of interest, especially so the other thing is that the trusted setup is there's a trusted part which is annoying, but there's also the part that these things are expensive and complicated to run. And so if you have a smart contract, in theory you can imagine smart contracts and they'll say I have a different circuit for each smart contract, right? And then that's not workable because you would need to do a trusted setup for each contract, which doesn't scale. So instead of that, you could create a generic contract, which is going to take some sort of assembly. So as its input, you will have the data, but also a program that it executes, maybe the code of the contract. And to make that efficient, what's interesting is that you will need to design a language that is good at representing the type of thing that you do in smart contracts, but also good at compiling down to, say, an arithmetic circuit, for example. And there's a nice trade-off to look at here, to find here. There may be a programming language that compiles very, very well to this, and on top of that is a good way of representing computation. So, but that like maybe you get like an order of magnitude like this, but I think we need several to be happy. And I don't know if we're talking about SNARKs today at all, because the thing is SNARKs, but SNARKs, which do essentially the same thing. They have bigger proofs, but they are faster to prove, which is interesting. There's a big gain here. Still slow.
SNARKs are SNARKs.
Yeah. The other side of it is like
SNARK is branding for SNARKs without trusted setup.
Sorry.
I say the SNARK is branding for SNARK without the trusted setup. The T is for there's no trusted setup.
Right. Yeah.
Transparency.
Maybe Howard, if you don't mind, I can just add something to what Arthur is saying. Well, one interesting, it's interesting what you said about outsourcing the proofs. You can also do this even if you care about privacy sometimes by somehow encrypting the parts of the data that you want to keep private, and then having the prover prove something about the encryption of some data. In some cases, that's possible. And also, maybe we'll talk about it later, but there have been a lot of recent developments with universal setup SNARKs, so that you can sort of just have one setup and then do whatever circuits you like, so you don't have to pay for the efficiency.
What's the current kind of practicality of using zk-SNARK protocols that have universal circuit, like support for universal circuits? Are these?
Yeah. So okay. So as far as I know, sorry, Howard, you broke up a bit for me. Do you mind repeating your question?
Oh yeah, I was saying, in terms of like the current practicalities of it, like I've also seen some of the research work here, and I'm curious, from your point of view, is it something that we can just launch today? Should someone just launch it today? What are the next steps towards getting ourselves to something that is actually a universal CRS for general circuits, etc.
I mean, so there are a few schemes floating out there. As far as I know, the only one that has an implementation is Sonic. My understanding, and we tried running it a little bit. I think it's about it's maybe like 1 to I don't want to say exact numbers, but I think it's like within the neighborhood of 1 to 4 times worse than like Groth 16 for similarly sized circuits. So, I mean, that's sort of practical. That's probably for a lot of applications good enough. In terms of what the barriers are, I think Sean is working on doing a setup. So I don't know, you'd have to ask him, I guess.
Yeah, I also saw there was like the Lego SNARK paper, but outside of that, I haven't seen so much developments. Like at least when I was looking at the performance on Sonic, it seems to be like they're doing these like batched proofs, and so there's like they take 100 proofs and try to do a batch verification, and then they amortize the cost across them. Whereas like first proof seems to be the longest or slowest running one, and from there all the rest are much quicker to check. Seems something that will be nice in the broad context currently, but like it's not effective just single proofs. From the can you guys hear me?
Yep.
Okay, yeah, my internet said it was unstable. It seems like there's a few general themes here. zk-SNARK seems to be useful in blockchains specifically for privacy. It's for scalability and also on interoperability. I'm curious, as these things start to get incorporated into these protocols, do you think that it will effectively disrupt existing blockchains like Bitcoin, which don't use zk-SNARKs, or do you think that they're at odds with each other and only one can ultimately win, or how do you kind of see that landscape going?
I don't think only one can win. I think, you know, the way that things have gone, there's a lot of technology sharing, right? So if one person makes a development, you know, everything's open source and free. Well, mostly everything. So you know, there's no real barriers in that sense. Usually the barriers are more in like I don't know, like what the desires of each respective community or community of developers, even more frequently, or miners, stakeholders in general, what their desires are. So you know, it comes down to that. I don't know.
Yeah, like when I think about it, it's like, you know, right now the application it's for something like Bitcoin are also very much it's in the store value bucket, where it's not really used for, you know, immediate in-store payments, right? And like I feel like perhaps you know, I also think that they're not going to be at odds with each other, but I think it lends itself to whole new verticals where, you know, perhaps point of sale kind of things actually become much more practical using a proof-based system here, especially if it's very fast or very cheap and it can be verified, you know, from the merchant side immediately on the spot. Yeah, like
that's true. I think you can also get a more seamless, like, say, in, you know, experience for a new user who maybe doesn't have like a wallet, or doesn't have, you know, isn't running a node or whatever, doesn't have a browser extension installed. If you're in a world where, you know, your chain is verifiable using a SNARK, then they can just, you know, that can run in a piece of JavaScript code that just grabs the SNARK and checks it, and they can already sort of be interacting with the system immediately. So I think in terms of lowering friction and providing a better user experience, there's a lot of potential there.
Yeah, I think it's nice to have more people be able to run Bitcoin on the full nodes essentially. I'm not sure it's going to make a big difference. I mean, you know, de facto today, what we see is that a lot of users who are not ideological or really into this, who are using these things, you know, not, you know, it's not even that they don't even run a full node, it's that they don't, like, a lot of them don't even self-custody their tokens. And so if you, and I, you know, it's like first gets them to self-custody, then get them to use a full node that they run, as opposed to you know, using someone else's node. And then if they start complaining that, hey, it takes me too long to sync a node. I mean, you know, the only people who complain today that it takes very, very long to sync a node are essentially developers who really want to run their own node and deploy locally. And that's about it. So I don't know that there's a lot of friction here. There's also the fact that I would say most projects today are moving towards proof of stake. And in proof of stake, you don't really have these guarantees that you have, you know, I touched on this earlier, that you have with proof of work currency. In proof of work currencies, in theory, the branch with the most total hashing power is a canonical one. And so, you know, in principle, you can just decide your thing for yourself just by saying it, you know, just by knowing the genesis block and looking at the weight of different branches. You know, in theory, I could receive SNARKs from a bunch of people saying, here's a head with that amount of total hashing power. Here's a head with that amount of hashing power, and make that decision. But with proof of stake, I can't do that anyway. I have to rely on a recent hash of something that happened. And so, you know, once I'm going to do that, once I rely on that hash, I'm probably not going to, you know, I don't have to download the whole chain. I can just download a snapshot and see where I am. So the whole synchronization thing becomes a non-issue. And of course, you know, out of historical reasons, I might say, well, you know, is this state that I have joined, you know, did it come out of nowhere, or did it at least follow a certain set of rules coming back from history? And it's important that you be able to do that. It's important that you be able to access old blocks and audit everything for yourself. But it's a very special kind of people who are going to want to do that. And some people want to do that, and they do a service to the rest of us by doing it. I don't think that most people are like, oh, you know, the reason I'm not using this is because it's so expensive to verify.
Well, yeah, I mean, I think probably the reason most people are not using it is because if you want to get started, you need to maybe download a piece of external software. So I think removing that barrier is useful. I guess it's also surprising to hear you say that it's not useful in the proof of stake context, because even though maybe you need to rely on a recent hash or something, it doesn't have to be something within, it doesn't have to be very recent. So it could be something, say, from a year ago. That's how we're setting it up with Coda, that the protocol is such that you only have to sort of be online once every year or so. The other thing is, in terms of data or syncing data. It's true that maybe you don't want to, or need to get all the data from, if you're only syncing to a snapshot from forever, but you still need to get all the data from since that snapshot, right? So depending on if you want to do 4 transactions per second or somewhat more, it will be a lot of data.
Yeah, I think my mind has evolved a bit on the matter. I used to think, so you start from the argument from Bitcoiners, which is that proof of stake is impossible because look, you cannot distinguish. You go online for the first time and you can't distinguish this. And then the first thing you're saying is like, okay, surely I should, surely like being able to know what the correct software to run does not require a lot less trust than knowing a hash that happened a year ago, right? And so you say, well, if I have to ask people to get a checkpoint once every year, surely it's a very small ask. And then you keep thinking about it, and then you realize that at the end of the day, these things are intended to be currencies, right? They have value because they're acceded by a bunch of people. And so, if you want to know what's the current head of the chain, you can look at different heads as different currencies in some sense. Different heads are currencies that are forked. And the right currency is the one that's accepted by the people, by the merchants. And so, you go to a merchant and they will tell you what currency they want to be paid in. And that gives you a tip of the chain. So maybe that argument doesn't really carry all the way to the very last few blocks. If you have, some latency in a network and you don't have finality in every block. But I no longer think that there's a big difference between asking, the snapshots to be yearly as opposed to hourly even. In Tezos right now, it's something like 2-3 weeks. You need to be online every 2-3 weeks. But I think the idea is that the 1 year thing is a reduction to absurd from the argument that proof of stake is impossible, because it's clearly possible to do this with 1 year. And I wonder where the limit is, and I don't think it actually needs to be that long.
That's interesting. You touched on a point where it's just about usage here, and right now, there's a set of coins that are, they're fully public in the open, and there's also coins like Zcash, which use zk-SNARKs to do confidential payments. I'm curious from your perspective, how do you see the adoption curve on these going? I think that it's a lot less contentious for projects that are developing coins that are, fully public for their financial payments to be adopted from, say, banking institutions or enterprises, or even just from different government jurisdictions. Do you find this to be a barrier for the general ecosystem for zk-SNARKs in integrating it into financial payments?
Arthur, I don't know, do you want to take that?
Okay, yeah, sure. So first of all, I would note that Zcash, is when Gemini decided to do Zcash, they had to ask approval from the New York Department of Financial Services, and which is the strictest regulator in the world. They got this approval. So even though sometimes people say oh, these coins are not going to be approved, you won't be able to do these things and declare. I don't think that's necessarily true. And one of the reasons is the ways that they did viewing keys is actually very well thought out. Because the idea is that instead of just publicly broadcasting a transaction to everyone, it's private by default. But of course, if tomorrow a judge comes and say we're investigating you, I'll show you, show us your transactions, and you say, of course, here are my transactions. If the IRS comes knocking down your door and say, show us your transaction, you can. But you choose to do so, and it's not
good. How are you?
Oh, sorry, but it's not unique to Coda. I mean, most things, most papers, you have your emails, all of that. It's not like your email are public by. Imagine every email were public by default, and then you were like, oh my god! But if we ask emails to be private, how are we going to know anything that's going on? It's totally normal for current transactions to be private. Now, that doesn't mean that people are necessarily going to be reasonable and not try to crack down on those. But at the end of the day, we have to look at why are we creating the systems for, and the fact that it's open, and the fact that privacy, I think, has been at the root of this movement for a long time. And if you had to choose between privacy and adoption, I think the right choice to make is actually privacy.
Do you think policymakers are comfortable with this notion of giving users this full privacy? You mentioned the viewing keys. Does that mean that we should have services like centralized services that will effectively be the keep a copy of the viewings, disclose that? Do you think these things should sit with the users? Like, how much should users really own their own transactional history versus a third party here?
I think it should be the same as mail or email. It's like your private correspondence. There are legal situations where you have to disclose your private correspondence, but by default it's private. And it's not the case today that somehow when you set up a private email server, you have to like get some sort of reporting or anything like that. So, I don't think it makes sense for private people who do transactions with other private people to have to report their transaction. It's different if you're like a public company, of course, obviously, maybe that's different. You need to have accounting, you need to have audits, and so on and so forth. But like for private individuals, there's no justification for making people disclose that part of their lives.
I mostly agree, but I maybe wouldn't go as far as Arthur. I agree that things should be private by default.
When it comes to the this notion on privacy and offering it, especially in crypto, it's a really dangerous. It's a very powerful and also very dangerous tool. Like a lot of people worry about the common issues which even on public chains is a common issue of like just what if people build nefarious markets, or if they open up programmatic logic for very dangerous things. And this is something that once you add privacy on top of it, it starts to cascade, because not only is that logic from an operational standpoint being hidden, but it's also the participants and the amounts and the type of actions that are happening that can all be fully private. In my view, it's like I obviously stand for privacy. I think that it's something that should be a core a core principle or feature that is built into a lot of these public networks. But at the same time, like there seems to be a balance that needs to be struck to enable the right type of compliance for policymakers or regulators in this space.
I definitely agree with you, Howard. I mean, there's also the fact that we already have nefarious markets which operate in the open today. So how new of a problem it is not obvious to me, but
I would also say that the main problem is the same problem as cryptography. The main problem is that if you make something, if you force something to be transparent to the good guys, it's also going to be transparent to the bad guys. And so, if all of your economic transactions, if all of that is essentially, semi-public, then, people and that could be privates, it could be organized crime, it could be foreign governments, or even your own governments could basically do bad things to you because they have access to this information. And unless you make it private, you're not going to be able to protect yourself against that. So like, what if it's used by, you have to weigh in, what if it's used by some petty criminal, right? As opposed to, I don't know, let's take an example when, the government of Cambodia, the Khmer Rouge, killed most of their population. And at some point, because they decided that it was a good idea to kill the intellectuals, they killed everyone who had glasses. So what if the government has access to all your transaction history and now decides that, hey, you bought some books, you must be a dissident, let's kill you. There were about 500 million people who were killed in the 20th century by governments. So I would say if governments had a better track record of being ethical and not killing people, absolutely, I think the balance should be that, yes, we should give more power to the government to catch criminals. But the reality of the situation and of history is that people should be afraid of their governments. Governments kill people in very large numbers, and people deserve protection against that.
Yeah, and I would just add to that, it's of course not only governments, but also large enterprises of all forms, including, companies that affect the world negatively in more obscure, or should I say obscured ways. So Yeah.
Go ahead.
No. We can move on.
Sure. I guess going back to some of the more technical aspects around this, as we go into greater integration of zk-SNARK specifically in blockchains, what level should we be optimizing for? Should we be thinking about the actual protocols, like for example, with this contest we're using Groth16, right? Should we be trying to optimize specifically for this protocol, or should we be trying to optimize on a lower level? What can be lent and reusable, for future iterations and for future integration, so that on public chains we actually, in the broad sense, maintain support for zero knowledge proofs, in general going forward.
I mean, I guess the thing is, most of these say, okay, if you want to take all pairing-based SNARKs first, they all basically do the same kinds of operations, which are basically, they do some kind of Fourier transform over a finite field. Please Google that. You can take a moment. And they do multi-exponentiations in some elliptic curves. So if we picked Groth16, I guess, because that's what most people use these days, and it's kind of a good proxy. But at the end of the day, if you're optimizing these two things, you can take the gains that are made and apply them to whatever pairing-based SNARK you might be interested in. In terms of SNARKs, yeah, I guess they also do FFTs, also over over finite fields. So I mean, in general, we're trying to implement parallelized implementations of finite field arithmetic. I don't know. That's the lowest level, but I think it's fine to pick a proxy and just do that and try and make good libraries with that can be reused later.
How about go ahead.
I would largely agree, and I would say, and maybe you can get a little bit with optimizing compilers, possibly. If you can find circuits which are equivalent but slightly smaller, that's useful. At least if you're not hand optimizing your circuits.
Well, why is it so difficult to optimize from a general programming language down to circuits? Maybe for people listening, it sounds kind of straightforward. Like, why don't you just compile it down and run it? Like, what's the trade-offs from that versus just hard wiring?
That's a very deep question. I mean, there's a, well, I don't know. I mean, there's maybe a complexity theory answer or something. The problem of finding the minimal equivalent circuit is difficult. Why is it difficult? Because you're well, I don't know how to answer that. I guess I don't know.
Sure.
Want to say something?
It's difficult because if you could do this, there's so many cool things that you could be doing. You could write a very inefficient algorithm, like a trivial algorithm that looks for any So imagine you have a problem, and I write a program that is going to check every possible solution, and I write this as a giant circuit, and then I say, okay, make that circuit as small as possible. So if you could do that, you could solve almost any problem you want in the world very efficiently, and so it's very unlikely that you can do that efficiently. But you can optimize you can do some optimization of some circuits. And also, to go back, it's true that the proving is really like a lot of really base operations like pairing, exponentiation, FFTs, and these optimize probably very well in hardware, and they parallelize. So I do have some hope with the hardware stuff.
How about for elliptic curves? Do you think this is something that we should try to find or pick a handful of curves that we define publicly and allow for different blockchains to just say these are the final curves that we should be using, or should these things be ever evolving?
I guess in my experience, it seems like different people have different requirements for their elliptic curves. So we're in a period of storm, I guess, now, in terms of people just going in many different directions and constructing curves which are suited to their purposes. As I mentioned, well, okay, so in Coda, we need some elliptic curves that have very special properties. But on the other hand, you pay some efficiency penalty for these properties, so not everyone would want to use them. In Zcash, they have their curve. It's pretty good, actually. There are some parameters that could be tightened there, but I don't know. I think it's best to agree on processes for generating curves rather than specific curves themselves.
Yeah, so I basically, like, when I think about a curve, I think like either I'm going to use this, either using the Zcash curve because it has a lot of nice properties. And one nice property it doesn't have, which is the one that that Coda uses, is that you can't easily make recursive SNARKs with it because it doesn't have this like this. It's not a pairing, but it's basically like the order of one curve is the same as the characteristic of the field of the other curve. And if you do that, you can do a lot of nice recursive SNARKs. The problem is that the only way we know how to do that is by having like larger keys than we would have otherwise. So it's kind of like one or the other, right? But I do think we should standardize on one, especially if hardware is going to be built. You really want to pick those parameters, like do a lot of soul searching on what might be the best curve for this, and then build the hardware.
Yeah, actually speaking on standardization, we just had the second annual zk proof standardization workshop, and I'm curious. Izaak, I remember you were there, and I'm curious from your perspective, what do you think has been beneficial from this, and also what are we missing? What do we need to talk more about? What should be brought up? Maybe there's separate tracks that we should discuss. Like for one, I didn't hear about much on hardware myself. Maybe there's other areas that you think are also missing.
I think the most useful part of this, at least for me, the standardization workshops has been just kind of doing a sync with everyone else who's thinking about this, about using SNARKs and in different capacities day to day. It feels it's good to sort of stay in sync about just what different people's requirements are. As you said, the issue of standardizing on elliptic curves or processes for generating curves. In terms of actually producing standards, I'm at this early stage, I'm less certain. I don't think that there's like the one thing that we can write down and say like, oh yeah, like Grot 16, like we're doing that forever. Yeah.
Yeah, like it seems like with the standardization effort right now, we've finally gotten very nice nomenclature, very nice conventions in place, which is super important for the community. And like my hope is also that we start to replicate or at least like demonstrate this within the implementations themselves to start to account for them. That's something that it's necessary on a low level, but it's also then effectively represented on a higher level with DSLs and whatnot. Without having this type of convention actually make its way in, I also worry about the ability for browsers to actually start to use this stuff. We see the efforts on WASM, we see the efforts on trying to build binaries from different languages, and if we have zero knowledge proofs that are from different languages coming together in the browser, and you're trying to use this in a way that is interoperable, it doesn't work unless we actually migrate this into our implementations.
Yeah, I mean, it's funny, all the SNARK DSLs, they're all kind of doing the same thing except for XJ-SNARK, which is a little bit different, to varying levels, except that they all have sort of different names for things, and yeah, they're not interoperable at all, as you say.
Yeah. Very broadly speaking, what are we missing here from the zk-SNARK landscape today? It seems like there's a lot of interest. It seems like there's a lot of people trying to write the low-level libraries in different languages now. What do we need to do next? What do we need to bring on board the next 10,000 or 100,000 developers to start using technology?
Did you say 100,000 developers to use SNARK technologies? I really don't think you need that. I think you need to have a system that works, but at the end of the day, these systems work mostly like black boxes. And once they're in protocols, I don't think you need 100,000 of people to use that. It's pretty specialized software. I don't know if there's 100,000 people, something like it's much more common than a SNARK. We mentioned F50. Doing an F50 is much more common than that. You don't have 100,000 people who are like implementing F50 libraries or using them at a very low level. They use higher level constructs. And so I think it's like an Ethereum meme because, you always like advertise a KPI where you're doing best on. And so, they attracted a lot of JavaScript developers. And so they were like, we have so many developers, as if, it's like one metric to optimize for. So I don't think you need 100,000 people to develop SNARKs. I do think that you need to give people good high-level primitives so that they can build private transaction. You need to build blockchains which are efficient, which can scale, and you can do a lot of that with SNARKs. But it's going to be an effort worldwide that's probably going to be led by, maybe 1,000 people and probably not 100,000 people.
I guess I think it's a good, yeah. I mean, I think it's Howard, what you're saying, I guess probably I'll say something that Arthur agrees with, but maybe a little differently. So I think, Howard, what you're saying is a good idea. I mean, maybe not 100,000 people, but some large number. It's hard for me to even estimate. I don't even know how many, say, Python programmers there are. But as Arthur says, we can make tools for people to use SNARKs to build compelling and useful applications without having to know all the low-level details. So even now, I mean, you can use any of the SNARK programming languages without knowing what the SNARK constructions are. I mean, there is an abstraction boundary. Sometimes it's a little bit leaky, but I think as time goes on, we can build more specialized DSLs that just expose the functionality in terms of, what people want to put in their SNARK program that's necessary to them. They don't have to think about constraints or anything. Maybe they'll just have to think about hash functions and, integer arithmetic or something. And, I mean, I think at that point, we can make tools that are easy for people to use. I don't know if 100,000 people will use them, but yeah, I think like better tools and, more training needs to happen if we want people to build compelling applications for zk-SNARKs. But
yeah, like the point I'm trying to get at here is that we discussed on the programming languages and how we can compile these down circuits. It seems to be a very difficult task, right? And then what's the alternative? For the end developer, the last thing I would want is for them to be hardwiring circuits. Like I've gone through the pain myself, and it's a pain, it's a nightmare whenever you get like even just like one bit off. And moving to higher level abstraction seems to be the general trend, seems to be the right direction. But at the same time, it's also very restricting. Like you can only do certain things with it. You can only have certain sizes with it. You can only have certain functionalities built out of it. And how should we address this then? There are libraries that have kind of primitives that are built in, like gadget primitives, or you can extend them, but we haven't seen something that's very robust or really just widely accessible for developers or practitioners who want to use zero-knowledge proofs and zk-SNARKs specifically in their application.
I guess like my philosophy in terms of this would be, first of all, let me just push back on the notion that you can't have high-level programming constructs and also low-level efficiency. I think it is, in some ways, it's possible to get the best of both worlds, which is what's done in something like Snarky and also in Bellman. But I don't think that's enough for the typical end user. I think that's sort of high level enough for someone whose day job it is, say, to program SNARKs. For the typical end user, I guess, or like the typical user or the typical use case, actually, let me say, for programming with SNARKs, I think the right philosophy to take is to build higher level DSLs which do one thing. Maybe they only let you build CRUD apps using SNARKs, like certified CRUD apps or something. Make one per use case and try and capture as many of the use cases that way. I don't know.
I like the DSL approach, and in general, I think like layers of meta programming on top of each other is a way to build complex stuff that's going to compile down to something efficient.
Yeah, you ask two OCaml programmers, that's the answer you'll get.
Yes.
Cool. Well,
I will add one thing. I think one tool that's kind of missing, it's like, you use a tool like Snarky or Socrates or these languages. It's not that hard to build your SNARK. One tool that's missing is kind of like, run my own trusted setup tool, That will going to that's going to generate the MPC for you, and that's all parts of the ceremony and so on and so forth. You can't just like roll that out with a few clicks today. But compiling a circuit nowadays, compiling a circuit, testing it not that hard. Running a ceremony much harder. So if there were tools to make that, and personally I think that especially that's like the second ceremony that zk did with the power of Stoa and with a much larger number of participants, I think is a pretty good compromise in terms of like the trust that you have to put in the system versus the efficiency that you have, because today you look at other systems, but there are no system today that are really close in terms of efficiency, and I don't have a trusted setup, unfortunately. But it is still fiendishly hard to run a good trusted setup process. And if that were a little more automated, I think we'll see a lot more SNARK deployment and adoption.
So are you saying that maybe on Tezos or on one of these networks, we should be playing a coordination game where people actually will, in a decentralized network, run a trusted setup for some type of universal CRS, and maybe with that you can start to govern and take rounds and have people take turns, running an update on this?
Yeah, but I mean, the universal, a joint effort for a universal CRS would be very useful every time something gets brought up. But at some point, you're going to want to say, I don't want to pay, this like, you mentioned like 4x penalty for using the universal CRF. I want to get the fastest thing possible. Oh no, I have to run a trusted setup process. So if there were a way of making this easier, I think you'd see more adoption. So the way that Tezos is looking at implementing zk-SNARKs today, to be honest, is working off of the sapling library. So it's not about building a circuit; it's just using like the circuit that's been built by Zcash. And I would say that the main hurdle, like personally, is like it's not so much about the writing the circuit. Also, a lot of work went into writing that circuit for sure, but it's in running the ceremony. I think that is a scary part for anyone wanting to deploy SNARK.
Yeah, it's a huge operational effort. I think like even something, there are even extremely simple things that pretty much anyone with some, say, web programming experience could probably implement. Just like a website where people, there's maybe a list of active ceremonies or something, and someone can say, oh, I want to contribute to that one. And maybe they post their sort of contribution request to some blockchain, so that if the website operator tries to censor them, people can see that. And I don't know.
Yeah, I'll add one more thing that could be useful for this. So let's say you want to take part in a ceremony like this. The first thing you're going to do is that you're going to get you're going to go to a store and you're going to buy a computer sealed wrapped randomly in a random store. Typically, you're going to want to get a cheap computer too, like maybe a Chromebook or something like that. And so then you could say like, okay, and then I'm going to install Rust or Camel or any of this language and compile my whole tool chain. And now all of a sudden, maybe you have to download things from the internet, or you have to plug like a CD drive. It gets complicated. Whereas the one language that ships with every single operating system is JavaScript, because you have a browser that ships with every machine. And so if you have the code that you need to render in a trusted setup compiled to JavaScript on a USB key, today, whether you're using a Chromebook or a Windows machine, it ships with a hash. It does ship with a hash utility in command line, so you could like put the file, check the hash of the file, run it in the browser, and get the result. I think that would be pretty neat. If it could be that simple for someone to participate in the algorithm in a ceremony, and then have a way of reporting the data to a website, aggregating this. So like Izaak says, there's a lot of stuff that can be done that's like really about the UX of running this ceremony and the organization of it. How do you recruit participants? Maybe like a website to sign up to participate, all of these things. That I think would solve a lot of the organizational hurdle that happens. It's not so much about having the code to do the MPC. I mean, that's complex code, but it's there are people who have written code to do this. It's hard, but it's not impossible. But like making it easy to deploy is a challenge that does not necessarily require very strong cryptography skills. or at least not as strong as would be required to design the MPC to begin with.
Those are both really cool ideas. You know, for the people listening, after you finish the contest and you're all up to date and up to speed on you know, the intricacies of zk-SNARKs, maybe you should go and build one of these. These are great ideas, and you know, also we're out of time right now, and I also want to thank you guys for taking the time and just talking about.
Yeah, Howard, Arthur, and Izaak. This panel was really fantastic. Go ahead, Howard.
Oh yeah, just wrapping up, just saying, like, you know, please participate in the contest. You know, if Izaak, if you want to say anything about that, I think that this is going to be a very fun challenge going forward into phase 2, and you know, I'm really looking forward to hearing and seeing all the things that people come up with. You know, please share it and put things online, and also just make it readily available to people so that we can continue to grow this ecosystem.
Yeah, I mean, maybe I'll just say one thing. So first of all, thank you, Howard, and to the organizers and Arthur as well. So just in case anyone doesn't know, let me just like explain it briefly, because we've been talking about this contest. So right now, Dekrypt and Coda are running this SNARK challenge contest with support from Tezos and others. And the goal is really to generate much faster implementations for pairing-based SNARK provers and verifiers and other.
Uh-oh, I think Izaak.
Did we drop Izaak?
I think Izaak got his internet or something might have cut out.
We did lose Izaak. I'm Joel Krauska. I'm also from Coda, and you can find us all if you just Google SNARK challenge. We have a reference Git repo that's up, so we have CPU code that generates reference solutions, and we have found a few libraries out there that have already been written for finite field arithmetic using Coda. We also will accept submissions using OpenCL if you're that flavor of developer. But again, we have a channel in Discord. You can hop in there, ask questions, and we hope other people are interested in participating. Thanks.
Awesome. Thank you guys for all of this. This was awesome. And yeah, thanks everyone for joining.
All right. Thanks. Take care.
Thank you.